Hello, welcome to the Points of Topology NPTEL NOC course, live session 8. My name is Shavik and I'm working in Costume the Madras. So, this is the 8th live session of this Points of Topology course. So, before starting further, can anybody confirm? So, there is one student, Mr. Mustaq. So, Mustaq, can you please confirm whether am I audible and is the screen visible to you? Please confirm. Mustaq, please confirm whether am I audible and is the screen visible to you? Please let me know. Okay, I hope I'm audible and the screen is visible to you. In case there is any issues, please unmute yourself and let me know, okay? Because while writing, it's not possible for me to look into the screen. Okay, okay. So before starting further, please let me know, do you have any questions or a doubt from the previous session, or do you have any question or doubt from the assignment and all? Please let me know. Please let me know in case do you have any doubt or any question, or else we shall start something new today. Please let me know. So let me check everything is working fine or not. Okay, things are working fine. It's recording too. Okay. Okay, so it seems there is no question to ask. Okay, so let me start. So today we shall, so in the, so till now what we have done, till now we have done till now we have done, we have gone through basic topology as well as connectedness. Okay, so today we shall start the compactness, its properties, and we'll then find solve the problems. Okay, so let's start the compactness. Okay, so let me start the definition. So definition goes as follows: let X be a topological space. Okay, so let U be an open cover of X. Let U be open cover of X. Hold on a moment. Let U be open cover of X. That is, we can write X equal to union of U. U belongs to U. Okay. This implies then X is said to be compact if every open cover of X has finite subcover. So that means what? Every open cover of X has finite subcover, then X is said to be compact. Okay, that's what by notion, but that's what by compactness means. Okay, so now, so that's the definition. So there is some theorem. Well, so now next thing is that, okay. So the first, so these are definitions. First exercise is as follows. Well, so in matrix space, so I'm sure you pretty much has done matrix space as a real analysis. There, you have seen the closed boundary interval as compact. You may have seen those things. Okay, so let's not get into those. Hold a moment, please. Okay. Okay. So fine circle. Now, so for example, we have seen that closed boundary interval are compact. So that is called Heine-Borel theorem. Just I am writing the statement. So proof you can find in any metric space textbook. Okay. So Heine-Borel theorem is as follows. So the theorem tells that um, any closed boundary interval AB subset of R is compact. So this is the Heine-Borel theorem. You can find this in any textbook of analysis. Okay, so let's not get into the proof right now. So we have, so the next question is as follows. So the theorem is that, so an exercise example exercise, let X be cofinite space, that is X is a set having cofinite topology. Of course X is infinite set, we have to assume that other is cofinite topology, not making sense. Show that X is compact, that is in cofinite space, that cofinite topological space is always compact. That means what? You need to show that any open cover has a finite subcover. So you need to start with an open cover and you will show that it will have a finite subcover. So please try to think and let me know. So Mustaq, please try and let me know. Okay, please take your time. I shall get back within a few moments. Mustaq, are you able to figure out why is compact, or any guess or any idea? Please tell me. Please unmute yourself, let me know. No need to hesitate. This session is a problem solving session. So please try to uh, respond. Mustaq, do you have any idea? Okay. So let me uh, show. I mean, let me solve this. Okay. So let me write it down. So so how we'll do? So we need to start with open cover. So let U be an open cover for X. So start with an open cover. Okay, that's what the target was. We need to show that it admits a finite subcover. Correct. So say U is equal to, the open says the form U alpha, or alpha is some index. Okay. Now fix some index. Fix it. And consider U alpha naught. This is open. This implies X minus U alpha naught is finite by definition of cofinite topology. So let X minus U alpha naught can be written as X1, X2, Xn, correct? So that implies what? Now each of this xi will belongs to U alpha I for some I. So this implies X equal to U alpha naught, U alpha 1, U alpha n. So this implies what? The collection U alpha I is a finite subcover of X, correct? That's what our target is. This collection is a finite subcover of X. So that means what we have done, we have started with an open set and finally have shown that we have a finite subcover of X. So that's what target was. So this implies what? This implies X is compact. Okay. So that's how the argument is. So that's the argument. Okay. Now, okay. So the okay. So I hope that's clear, Mr. Mustaq. However, for co-countable topology, this is not the case. That is, let me write down the statement precisely. Co-countable topology is not compact. That means what? If you start with a uncountables with the co-countable topology, you will always able to come up with an open cover which does not admit a finite subcover. Okay, so try to construct. Open cover which does not admit finite subcover. So please try to do it by yourself. Take your time. I shall get back to you in a few moments. Mustaq, please try. Oh, well. Okay, so Mustaq, are you able to figure out? why the co-coordinate topology is not compact. That means what? In other words, you need to construct an open cover that does not admit a finite subcover. That's what you need to construct, right? So what is the open cover? So is it, so are you able to come up with any kind of open cover which might not admit a finite subcover at any cost? You may guess there's no issues. Well, so since you haven't responded, so let me explain. The solution is as follows. So let me construct the open cover, okay? So first of all, choose a countable set x1, x2, countable set in X. Okay. So define U1 to be X minus X1, U2 to be X minus X1, X2, U3 well, sorry, it's a mistake, X minus X2, X3 dot dot dot. U2 is equal to X minus X2, X3 dot dot. U3 is equal to X minus X3, X4 dot dot. Similarly, Un is equal to X minus Xn, Xn plus 1 dot dot. Okay. So these forms, these UY, this UY forms an open cover of X. Okay, this UY forms an open cover of X, correct? Why? Because if you choose any X belongs to X, and if X is not equal to Xi for all I, this implies X belongs to Uy for all I, and if suppose X equal to Xn for some n, that implies X belongs to X minus 1. Okay, so that means this collection Uys is an open cover of X. However, it shall not admit finite subcover. However, it shall not admit finite subcover. Question is why? Please think and let me know. Please take your time. Mustaq, please think and please let me know. Mustaq, please think and please let me know. Mustaq, are you able to figure out how this is coming? Any idea or any guess? Okay, so in that case, let me write it down. So, suppose it admits finite subcover. Suppose it admits finite subcover. So say u1, u2, sorry, not u1, u2, I have to write ui1, ui2, uin. Okay. So by definition, uij, but x minus xij comma xij plus 1 comma xij plus 2 plus and dot dot. Okay. However, xi1 minus 1, this thing does not belong to this union of aij. So that means what? So that means this collection uij, j is equal to 1 to n, does not admit finite subcover. Okay. So that's what the argument is. I hope it's clear. Now, okay. So now the next theorem which you're going to see is the following. Hmm. Just hold a moment, please. Okay, so it has a finite subcode. Okay, now, okay, so the next theorem is as follows. Every closed space of a compact space is compact. So every closed with compact space is compact. So please think and let me know. So that means, so you need to start the open cover and to show that it admits a finite subcover. Okay, it shouldn't be difficult. Please take your time. Please let me know. Mustaq are able to figure out how we can able to show that every compact subspace closed subspace compact is compact. Any guess? Okay, so let me prove this. So let if subset of X be closed and X compact. So let this collection of alpha U alpha be an open cover for F. Okay. Now that is F is a subset of union alpha U alpha. Now if is closed, this implies X minus F open. So this implies what? This U alphas, this collection union X minus F, this collection forms an open cover for X, correct? But X compact. So that means what? That means this open cover has finite subcover. Okay. So that means, so let the finite subcover be U alpha I equal to 1 to n X minus F is equal to X. So that means what? F lies into U alpha I equal to 1 to n. So that implies F is compact. Okay. This particular union U alpha tells that our chosen open cover U alpha has a finite subcover. Okay. So that's what that's how, I mean, that's why every in compact set, any closed space have a finite compact set is compact. Okay. So that's what the argument is. Now the next theorem tells that every compact sub of Hausdorff space is closed. Every compact subspace of Hausdorff space is closed. So please think and let me know how to do this problem. Please think and let me know. Take your time. Okay. Okay, so how to solve this? See, so it's quite tricky actually. Mustaq, are you able to figure out at least how to approach it, or any guess or an idea? Okay, so the solution is as follows. So let x be I'll drop a space and a subset of x closed. We need to show that, sorry, a subset is compact. We need to show that a is closed, which is equivalent to showing x minus a open. Okay. So now what we'll do, we will choose the x belongs to x minus a. It is x does not belongs to a. Okay. That means what? X not equal to a for all a in a. Okay. Now capital X is Hausdorff. So there will exist open sets UA phi A with A belongs to UA and X belongs to phi A, such that UA intersection phi A empty. Okay. Now consider the collection of UA belongs to. This collection forms open cover of A, but our by assumption A is compact, which implies this collection admits a finite subcollection. Subcover I is equal to 1 to n. This is covers A. Okay. Now define U to be union of UAI and V to be intersection of VAI. Okay. Now claim is U intersection V is empty. Of course, by definition, U contains A. So the point is, if some t belongs to intersection V, that means t belongs to UAI and t belongs to VAI. However, by construction, UAI intersection VAI empty. So that means what? EU intersection V empty. That means what? V sub of x minus a, and of course it contains x. So what we got? We start with the empty set, and that point belongs to x minus a. Find an open set V containing x, so that x minus V equal to empty. Correct. So that's what the target is. So I hope it's clear to you, Mr. Mustaq. So that means what? We started with an open set x and finally come up with a, sorry, we started with a point x lies outside capital M, and finally come up with open set lies outside capital A containing x. So that means what? That means x minus a open, which implies A is closed. Okay. So that's what the problem is. So that's what the solution of this problem. Okay, so that's the solution. So that's the proof of this theorem. Okay. Now, the next thing which we are going to prove is that continuous image of compact size is compact. Continuous image of compact set is compact. So that means what? You need to choose an open covered. So that means what? So that is if f(x) to y continuous and y compact, this, sorry, and x compact, this implies y compact. So please try to prove it by yourself. I shall get back to you, Mustaq. Please try to prove it by yourself. Ah, well. So, Mustaq, are you able to figure out how to approach this problem? Any idea or any guess? Okay, so let me prove this. Let me this for you. Okay. So what's the process? The process to do, so we have to start with the continuous function, which you already done, and Excel a domain is compact to show that if of x is y is compact. Okay. Okay. It's not y, it's to f of x. Okay. It's compact. So proof. Proof is as follows. Let u alpha be open cover for fx. So that means what? F of x sub of union alpha u alpha. That implies what? X sub of union alpha F inverse union alpha. So that implies what? F inverse u alpha that means F inverse. So to open now already know X is compact. So that means what? So we'll have a finite score. That means F inverse u alpha I equal to 120 the finite subcover for X, right? That implies what? X equal to union of F inverse u alpha I. That implies what? F of x sub of union of I equal to 1 to n u alpha I. That means what? F of x is compact. So we started in the open cover and then finally with an finite subcover so that the F is compact. Okay. So that's what the argument is. So I hope it's clear, Mustaq. So now the next exercise is that let f x to y by be bijective continuous if x is compact and y Hausdorff, then f is a homeomorphism. So Mustaq, please try to approach this problem. X compact y Hausdorff means it is a homeomorphism. So please think. So basically, the hint is that, so I must give the hint also, otherwise it's not directly possible. Show that f is closed to 1. That's the hint. So please think and Please try to figure it by yourself first. Ah, well. Hi, I'm extremely sorry. Due to some um, network issue, uh, I have to disconnect and rejoin. Okay, so hope now everything is working fine. So okay, so where was we? Okay, so we was trying to show that um, okay, so we was trying to show that um, okay, so let me start the whiteboard. Okay, so so it working? I don't know. It's why this makes things too small. I don't know why. I mean, why they are making these things. Okay. So this is what we are trying to prove now. Okay. We shall prove this. So hold a moment, please. I need to reshare the screen. Sorry for the inconvenience. Okay. So hmm, now things are working fine as we're understanding. Okay. So now we need to show that f is a closed map. Okay, so what is the process of showing some closed map? So hold a moment, please. Okay. So the point is that so in order to show if it's a closed map, what we need to do? Uh, okay, so let f, well, seems that it's reloading. So let me reload it. Okay. Okay. So okay. So we need to show if it's a closed map. So we'll start with the f subset of xv closed. We need to show f of f is closed in y. However, the x is given to be compact, so that and since f is closed, so we have already done a theorem which tells the closed subset of compact is compact. This implies f is compact. And now since little f is continuous, so this implies little f of capital is compact. Okay. And but the codomain y is Hausdorff. So that implies and compact subset of Hausdorff is closed. This implies f of f is closed in where? In x, in y. So that means f is a closed one. So what the argument is? Argument is nothing but to, so argument is nothing more than using the previous fact which we have already seen. Okay, x compact f closed, we have using the two facts, closed subset compact compact and in a and compact subspace of Hausdorff space is closed. So these are the two interesting and important facts which you are using for showing that our f is closed. Okay, so that's what the argument is. Okay, so I hope it's clear, Mr. Mustaq.
Yes.
Okay, thank you, Mustaq, for the confirmation. Okay, so now the next um, okay, now we are going to mm, now we are going to show that, I mean, okay, so the next exercise is as follows. So is not coming, hold a moment please. So the exercise is as follows. Let f(x to y) be continuous and plus y is compact Hausdorff. Show that the graph of f, that is x comma fx, is closed in x cross. So graph of f is closed in x cross y. You need to show. Okay. So okay. So please try to do it by yourself. Please take your time. Oh, wow. So Mustaq, are you able to figure out how to Mustaq, are you able to figure out how to approach this problem, or any guess for, or any idea? Okay, so the technique is as follows. So basically, what we need to do, we need to start an open set x. Sorry, we need to define a function h from x cross y to y cross y, with x and y goes to f of x comma y. Okay, that is h equal to f cross identity of y. That is our h. Now consider diagonal of y in y. Diagonal of y contain the elements of the form y comma y with y belongs to y. So in that case, how h inverse of diagonal of look like? It contains all those x y belongs to x cross y such that h of x comma y belongs to diagonal, and h of x comma y is nothing but what? Fx comma y over diagonal. That is same as saying that y is equal to fx. That is to say, we can write this thing equal all those x comma y belongs to x cross y such that y equal to fx. So which is nothing but what? X comma fx with x belongs to x. This is nothing but what? This is nothing but graph of f, correct? That's what the graph means. Thus, now, so that is what we got, graph of f equal to h inverse delta of y, and given y is house graph. So this implies graph of y is closed, and h is continued. This implies h inverse graph of y closed in x cross x. So that means what? So that means graph is closed in x cross y. Proved. So, Mustaq, is the argument clear? Please let me know. Mustaq, is the argument clear? Please let me know. Okay, so the next problem is as follows. If y is compact, subspace of Hausdorff space X, and x naught is a point not in Y, then there exists disjoint open this U and V containing x naught and Y respectively. That means what? If Y is compact and Hausdorff space and x naught does not to Y, then we shall always able to get a disjoint open sets containing x naught and Y respectively. Okay, so that's what I need to do. Okay, so please try to figure this out by yourself. Take your time. Mustaq, are you able to figure out how to approach this problem or any case scenario? Mustaq, any guess or idea for solving this problem? Okay, so let me explain the argument. Okay, okay, so see. So since so we have already seen the following. First of all, we have one already seen the following. I mean, we have already proved the following, that if y Hausdorff and f subset of y be close compact and x naught does not belongs to f, then there exists disjoint open sets. Then there is disjoint open sets U and phi of x with x belongs to U and f sub of phi, and U intersection be empty. So this fact we shall use it now. This is the hint and this is the main technical key. Okay, now we are going to use this to prove our desired result. Okay, so just hold a moment, please. Well, it's working, it's not working, I guess. Okay, so the thing is that the hint is as follows. There is no one. Okay, so so first of all, one. So all these problems, sorry. So first of all, one minute, what happened? Okay, so So basically what we will do, we need to use the Hausdorff. So x naught does not belong to y. Okay, that implies what? X naught not equal to y for all y belongs to y. Correct. So that implies there exist open sets ux vx of x with x containing ux. Sorry, yeah, with x containing ux and y containing vx such that ux intersection vx empty. Okay, now recall that y compact and the collection vx, this collection vx is an open cover of y. Now this collection vx is an open cover of y. Okay, now uh now and so vxi I equal to 1 to n be a finite subcollection okay, and so y equal to union of vxi I equal to 1 to n. Okay, now we are defining v to be, sorry, union of vxi I equal to 1 to n and u to be intersection of uxi I is equal to 1 to n. First of all, by construction, this our v contains y, and of course u contains the point x dot. Our claim is that u intersection v empty. How to prove this then in that case? So Musta, can you please think and let me know how to show that this particular thing is the intersection is empty? Any guess or an idea? Please take your time. Any guess or an idea how to approach this problem? Please take your time, let me know. So now suppose T belongs to U intersection V. So by construction, what T belongs to Uxi and T belongs to Vxi. But by construction, Uxi intersection Vxi empty. So that implies what? Such a thing is not possible. So that implies U intersection V is equal to empty. So that implies X belongs to X minus F sub of X. Sorry, X belongs to phi sub of this. So that means what? So that means, I mean, that's what we need to show, that X minus F is open, right? So that's what our target is. Is the argument clear, Mr. Mustaq? Is the argument clear, Mr. Mustaq? I hope so. Okay, so now let me go to the next problem. The next problem is as follows. Okay, so there is something called finite intersection property. Okay, just hold a moment, please. So finite property is what? A collection C of subsets of X is said to have finite intersection property, in short AFIP. Okay, if every finite subcollection C1 C2 of C having non-empty intersection. This is what by finite intersection property means. Every finite subcollection have non-empty intersection. Okay, that's what the property means. Okay, So the first theorem is that so the next theorem tells that the theorem tells that theorem result whatever you can say, there is no issues. X is compact if and only if every collection C of closed sets having FIP has non-empty intersection. Compact if and only every collection C of closed sets having finite FIP has non-empty intersection. That's what the FIP means. Okay, I mean that's what the theorem is. So yeah, so please think and let me know. Mustaq, please try to do it by yourself first. Please take your time. I shall get back to you after a few minutes. So please try to do it by yourself first. Please try. Oh, so let me do the one direction, and the next or reverse direction you can do it by yourself. So let intersection C belongs to C empty. So that implies what? Union of x minus C belongs to C whole of x. That means the collection x minus C is an open cover of x, but x is compact, so it will have a finite subcore. So we can write x equal to union of x minus C I equal to 1 to n. This implies what? Intersection Ci I equal to 1 to n empty. But that is not possible because as the collection C has FIP. Since it has FIP, so such a thing is simply not possible. Okay. So that's what the argument is. Okay. And and reverse direction, you please try it by yourself. If you are unable to solve it, please let me know in the next session. So in the next session, we shall continue with various properties of this compactness, and then we will solve again some interesting problems. Okay. Thank you.